All right, guys, how you doing? This is our last video in this intro to reactions, stoichiometry, the math of chemistry, and we're going to be talking about the empirical and the molecular formula today. Okay, and we'll be doing some questions here, but most of our questions will be done in class. All right, as classwork. So we're able to calculate the percent of a compound by the mass of each element. We worked on that on our last video. Go back and review it if you need to. That's going to help us identify unknown substances. So first, we've got to identify the ratio of the number of moles of each element in the substance. So once we have this formula based on a whole number ratio, this is something we call the empirical formula. So the empirical formula indicates the molar ratio of each element present in a molecular compound reduced to the least common denominator. So the empirical formula for benzene, C6H6, is CH. Now how do we do this? We get the mass percent of the elements. We did that on the last video. Then we can assume, since we're talking about a whole formula, that there's 100% of each of those elements. So we're going to assume 100% or 100-gram sample. Then we just change the percentages to grams of each of those elements. Okay. Then we use the molar mass of each of those elements to determine the moles of each element. Then we calculate the mole ratio, and from that we get our empirical formula. Now, there's only one empirical formula for a substance, but two different substances can have the same empirical formula. Now, why is this? It's because the empirical formula is based on the ratio of the elements given in the lowest common denominator. Let's look at some examples. We've got hydrogen peroxide, things that bubble out of our cuts. The molecular formula is H2O2. But if we took the lowest common denominator, that empirical formula would be OH. Hydroxide. The molecular formula is OH. It's an ion, OH minus. The empirical formula for hydroxide, of course, is OH. So, question for you. The empirical formula for C6H4NO32 is, well, that. Well, we've got to simplify it, make sure we're talking about the same thing. So, we're going to have to convert some of these things and multiply and distribute things out. Switch to my pen. So, I've got C6, I've got H4. So I'm going to have to distribute that too, because I got two nitrates. So I've got two nitrogens, and I've got six oxygens. So I need to find the lowest whole number ratio. So my lowest one is 2, so I divide everything by 2. That's going to give me C3, yep. H2, yep. N1O3. That's false because it's not N2. Okay? When I distribute that 2 over there, that's N2. And that's the lowest one. Okay, so that would be false. Which formula has an empirical formula that is the same as its molecular formula? So we're going to have to do the same thing here. That's CH2, Cl. That could be 3. That's going to be N2H8. C. No, that's not going to be it. I'm going to say all of them because all of them have 1. The carbon there, the nitrogen there, chlorine there, they can't be divided. So I'm going to say D. and it is D. All of them have it. So how do we calculate empirical formula? So I'm going to work through this. So PABA, or para-aminobenzoic acid, if you look at a bottle of sunscreen, it'll say PABA. This is what it is. It's got a carbon, hydrogen, nitrogen, and oxygen. The percentage of carbon is 61.31%. The percentage of hydrogen is 5.14%. And the percentage of nitrogen is 10.21%. And oxygen is 23.3%, 33%. If you add all those up, guess what you're going to get? 100. So, how do we do this? First, we're going to convert the mass percentages, which were given, to the mole amounts in a hypothetical 100-gram sample. How can we do that? If we add up all those percentages, we get 100. So if we say those are grams, all right, we add all those up, we get 100. So I get 61.31. And formally, we're going to multiply it by 100. Or we get 61.31 grams. You can see that one of the things I do is I just go ahead and know I'm doing that and make those percentages grams. Either one's okay. I'm not going to count off if you don't. But make sure you understand what you're doing. That's the key. So now we've got to get those grams into moles. Let's go back 2 videos over. If you need to, use the mole roadmap. So now we know the masses of this sample of 100 grams. We got to convert these into moles. So I'll use my periodic table, and I'm to see that the molar mass of carbon is 12.01. So 1 mole over 12.01 grams is the molar mass. I do the same thing for hydrogen. I use 1.01 from the periodic table. Nitrogen, 14.01. Oxygen, 16 grams. Okay. So now I'll start doing my math. Oops, I think I see an error. 23.33 divided by 16 is 1.458. I'm going to have to put my pen on. And I'm going to have to correct that slide, because that would mess me up. So that's 1.456. 1.456. I got 458 on my calculator, rounding errors. Okay. So that gives us the number of moles. So they corrected it there. That's good. So now that we've got the number of moles, we're going to find what the mole ratio is by dividing the mole value by the one with the smallest number of moles, which would be that one, 0.728. That's the smallest number of moles in every one of these. So I'm going to divide 5.105 by the moles of nitrogen. That's going to be the smallest one. And I get 7.005, so I can say that's 7. 5.09 divided by 7.288, I get that. Well, that's really 7. 0.728 divided by 0.728 is going to give me 1, of course. And 1.456 divided by 0.7288 moles is going to give me 2.001, or 2. So I can write the empirical formula now. The lowest whole number ratio is 7 C7H7NO2, using those numbers there. 3 steps to get to the formula. And y'all have got the tools to do it. So here is 1,6-diaminohexane, and they use this to make nylon. And we see that, here's another example. The carbon is, in this formula, is 62.1%, hydrogen is 13.8%, and nitrogen is 24.1%. What's the empirical formula? Use our steps. So we went ahead and just did the little shortcut. So I got 62.1% multiplied by 100, 62.1 grams, 13.8 grams, 24.1 grams. Think about where I got those numbers from. Took those percentages and made them grams. And they add up to 100. So convert to moles using the molar mass from the periodic table. And I do. And so I divide 62.1 by 12, I get 5.17 moles. Hydrogen, 13.8, I get 13.8 moles. 24.1 gram divided by 14.01, I get 1.72 moles. Then I'm going to find my lowest mole amount. And I'm looking at 5.17, 13.8, it's 1.72. So then I'm going to divide every one of those by 1.72 to get that ratio. And I get 3.01. That's really 3 if I round. 7.96, I'm going to round to a whole number. That's 8. And of course, that's going to be 1. So my empirical formula for 1,6-diaminohexane is C3H8N. Not hard. We'll work this in class. What's empirical? We'll work this in class because these are classwork things. Now, this works pretty well for most compounds, but sometimes the math will give us not a whole number. So I'm looking at iron something oxide. I don't know if it's 2 or 3. So I get the mass of the elements, mass percent. I get 69.92, 30.908. I divide through by the molar masses to get the ratios. Then I got 1.25 moles here and 1.88 moles. I use this because it's my lowest ratio. That gives me a 1, and 1.88 divided by 1.25 is 1.5. Ooh, I really can't round that to 1, or I can't round that to 2. And I can't use 1.5, that's not like a whole number. So how would I make 1.5 a whole number? Multiply by 2. If I multiply that by 2, I'm going to get 3. That's a whole number. Well, then if I do it here, I've got to do it there. So that gives me the ratio of 2 and 3. So the empirical formula is Fe2O3. And of course, that's going to be iron 3 oxide, as we learned from Unit 4. We'll work this out in class. That too. So, hydrates. And I'll give you an example of this in class. Many ionic compounds will have a fixed quantity of water molecules in their structure. We call these hydrates. And the formula, and this is copper sulfate, pentahydrate, its full name. So when you find these in nature, these crystals, it'll have 5 waters of hydration is what we call it, 5 H2Os. And it'll be in there. And if you cook this stuff off, the water off, you'll come up with a white powder. Leave it out in air, it'll absorb water and it'll turn blue again. So the mole ratio of water to the dry copper sulfate is 5:1. All right. How do we find the waters of hydration? All right, we can find the formula by heating it up to remove the water. Then we can find the mole ratio between what was left, the dry crystal, and the water, just as if you're going to find the empirical formula. Same thing. Okay. So when we heat mag sulfate, we found it to be roughly 51.3% water by mass. 51.3% of the weight was driven off. So what's the formula of the hydrate? 100%, right? So 100 minus 51.3 is 48.7. That would be the mag sulfate. So on a raw sample, we would have 48.7 grams of mag sulfate, 51.3% of grams of water. Convert everything into moles, and we do. We come up with 0.405 moles of water, and Then we do that by the molar mass. We get 2.85 moles of water. All right. Find the formula there. We're going to divide by, let's see, the lowest one, 0.405 moles of mag sulfate, 2.85. That shows me that I've got 7 moles of water in a sample of mag sulfate. We'll do this in class. Now, we've been talking about empirical formulas, and that's great. All right. The molecular formula will indicate the number of atoms of each element present in a real molecule, not the empirical formula. The empirical formula for an ionic compound is also the formula compound. The molecular compound may not be that lowest whole number ratio. So the molecular formula of a compound could be the same, or it could be a whole number multiple of its empirical formula. This is what we mean. So I've got CH, that's the empirical formula. It's got a molar mass of 13. All right. C2H2, ethene. All right. It's got the same empirical formula as CH, but it will have a molar mass of 26. Benzene, C6H6, the molecular formula. It'll have the molar mass times 6, that whole number ratio, that whole number multiple. It's going to have a molecular mass of 78. And you can see in the other examples of methanol, all right, that would be both empirical and molecular. Ethanoic acid, that's molecular because you can see that's not the lowest whole number ratio. And it's going to have a different molar mass, 2 times the empirical formula. And glucose, C6H12O6, that's a molecular formula because it's not the lowest whole number ratio. And you can see that it's going to be a multiple, all right, a whole number multiple, 6 times the empirical formula molar mass, or a 180. Just the way it is. So to find the actual formula of a molecule, okay, we need one other piece of information: what the molecular mass is of that molecule, which we can determine with instruments, or I can give it to you in a question. If you know the ratio of the elements in a molecule and you know the total mass of the molecule, then you can determine the molecular formula. This is how we do it. So we know the empirical formula of CH2O, and it has a mass of 180 grams per mole. So to get the molecular formula, find what the molar mass is of the empirical formula. CH2O is going to be 30 grams per mole. Carbon is 12, 2 hydrogen is 14, plus 16 for oxygen is going to be 30 grams per mole. Then we can divide the molecular mass, 180, given to us by the empirical formula mass calculated, and it's going to be have a multiple of 6. So then we multiply the empirical formula ratios by 6, and we come up with C6H12O6. So we'll do some of these in class: empirical formulas, the percentage compositions, and the molecular formulas. And make sure we have a good understanding of them before we go into hardbound stoichiometry. Okay? So anyway, this is Coach Scott saying have a great day. This is the last video in this series. And we'll make sure you understand this, have a good understanding, and move on. So anyway, this is Coach Scott saying have a great day.